You know, when we talk about AI language models today, you probably picture two really different types. On one hand, you've got the GPTs of the world that write just like we do, one word after another, from start to finish. But then there's this whole other approach, these diffusion models that act more like a sculptor. They start with just a block of random noise and somehow carve a perfect sentence out of it. They seem like they're from totally different planets. But what if I told you they actually share the exact same DNA?
Okay, let's really break this down. The autoregressive models, the ones we're all pretty familiar with, they build their answers sequentially. It's like they predict a word, tack it on the end, and then predict the next one based on everything they just wrote. But diffusion models, whoa, they start with complete chaos, total gibberish, and then they refine the entire sentence all at once over and over again until a clear idea emerges. I mean, on the surface, you couldn't imagine two more opposite ways of doing things.
So what's the deal here? Are these two approaches fierce rivals, just competing ideas on how to build AI? Or is there a secret connection, some hidden piece of code that links them both? Well, to find that answer, we've got to go back to the very beginning.
To find that link, we need to hop in a time machine and set the dial for 2017. See, the AI explosion we're living through right now, it didn't start with some grand ambition to create chatbots or artificial consciousness. Nope, it started with a much more practical, almost humble problem. How do we get better at machine translation?
And the solution they came up with was an architecture called the transformer. Its original mission was not to be a general, all-knowing AI. It was built for one job and one job only, to solve what's called a sequence-to-sequence problem. You give it a sequence of words in, say, English, and it gives you back a new sequence in French. That's it. But that one simple blueprint, well, it turned out to be more powerful than anyone could have imagined. The original transformer had two distinct parts that worked as a team. First, you had an encoder. Its job was to read the entire English sentence and build a really deep contextual understanding of it. Then, it would pass that understanding over to its partner, the decoder. And the decoder would use that context to generate the French translation, one word at a time. Simple, right? One part to understand and one part to generate.
The paper that introduced all this had this now famous title, and it really points to the secret ingredient here. The big idea wasn't some brand new mechanism nobody had ever seen before. It was about taking an existing idea, called attention, and basically promoting it from a tiny background character to the main star of the whole show. And that was the breakthrough.
Now here's the crucial part. Those two halves of the transformer, the encoder and the decoder, they use this attention thing in fundamentally different ways. The encoder used what's called full self-attention. To understand any given word, it could look at every other word in the sentence, forwards and backwards, total context. But the decoder used causal attention. When it was generating a new word, it was only allowed to look backwards at the words it had already written. And that one single difference is the key to this whole story.
And this is where the plot takes a major turn, because researchers pretty quickly realized, hey, wait a minute, the encoder and decoder are great as a team, but they're also insanely powerful all on their own. You didn't always need the whole package. You could just grab one of the parts and use it for totally different things. And that led to a great split, a fork in the road for the entire field of AI.
So the first branch to emerge is the one we're all super familiar with today. Researchers took just the decoder half of that original blueprint, and from it, they created the generative pre-trained transformer, or, as we all know it, GPT. And just like the name says, it was built to generate stuff. The way GPT learned was by playing a really simple but powerful game, next token prediction. You just feed it the start of a sentence, and its only job is to guess the very next word. And the decoder's causal attention was perfect for this, right? By its very design, it can only look at the past, which is exactly what you need to do if you're trying to predict the future, or, the next word. At pretty much the exact same time, another team of researchers took the other half of that original blueprint, the encoder, and they built a totally different kind of model. This branch, led by Google's BERT, wasn't about generating pages of text. It was all about deeply, deeply understanding the context of language. So BERT's training game was completely different. Instead of predicting the next word, it played fill in the blanks. You take a sentence, hide a few words with a special mask token, and then you'd ask the model, hey, what's missing here? And for this task, the encoder's full self-attention is absolutely essential. To make a smart guess about a missing word, you have to be able to see the context from both the left and the right.
And this wasn't just random. The researchers found there was a sweet spot for this fill-in-the-blanks game,
A masking rate of about 15% was just right. It was challenging enough to force the model to learn really complex patterns in language, but not so hard that the task became impossible. BERT became a true specialist at this one particular skill.
So there you have it. The great split was complete. That original transformer blueprint had now split into two very distinct families. You have the GPT-like models, using the decoder to predict the future with causal attention, and you have the BERT-like models, using the encoder to understand the present by filling in the blanks with full self-attention. And for years, these two paths just evolved in parallel.
But what about those weird diffusion models we started with? The sculptors. Where do they come in? Well, this is where things get really interesting, because we're about to have a very surprising family reunion. It turns out they aren't some totally new species of AI after all.
Believe it or not, diffusion models are the direct descendants of the BERT and encoder family. So those two rivals from the very beginning, they're not rivals at all. The sculptor is actually the direct intellectual heir to the model that was designed to fill in the blanks.
So, how on earth does that work? Well, just think about the process. A diffusion model starts with the entire response being nothing but mask tokens. It's 100% noise. Then, it basically just does BERT's job. It tries to fill in all the blanks at once. Of course, most of its first guesses are pretty bad. So, it remasks some of them and tries again, keeping the good guesses and refining the bad ones. It just keeps playing fill-in-the-blanks over and over and over, with less and less noise each time, until a perfect sentence is sculpted out.
And the key that makes all of this possible is one crucial difference in how they're trained. See, BERT was a specialist. It was trained to solve the fill-in-the-blanks problem at one fixed difficulty, 15%. Diffusion models, on the other hand, are generalists. During their training, they're shown examples with a completely random amount of masking. Sometimes it's 90% masked, sometimes 50%, sometimes 10%. This teaches them to be masters of denoising at any level, which is exactly the skill they need for that sculpting process.
Okay, let's pull all these threads together now. We started this whole journey looking at what seemed like two completely different kinds of AI. But when you actually trace their family trees, you find that they all come from one single elegant blueprint, one that was originally designed for a totally different job.
So our story kicks off in 2017, when the original encoder-decoder transformer is born. Just a year later, in 2018, it splits into two paths, the generative GPT branch and the understanding BERT branch. And that brings us to today, where we're seeing this amazing reunion, as the ideas from that BERT and encoder branch have now given us this powerful new diffusion approach. It's wild. One single idea has spawned an entire empire.
In the end, it's pretty incredible. This one amazingly versatile idea, originally designed just to translate languages, has turned out to be flexible enough to power every single major AI language model we use today, whether it writes word by word like a human or sculpts from noise like an artist. And that leaves us with one last, really fascinating question. If this single blueprint could build an entire empire for language, what will it build next?